So we have already discussed what is self-induction. Now mutual induction. What is self-induction? If there is a single coil and if current is passing through that coil, EMF is developed in the same coil, then that is called as self-induction. But mutual induction means there will be two coils placed adjacent to each other. Here this is self-induction, only one coil if you take. Current is passing through this coil and EMF is generated in the same coil, then that concept is self-induction. But if there are two coils like this placed very close to each other, when current is passing through this coil, if EMF is generated in the other coil, or when current is passing through this coil, if EMF is induced in the other coil, then that is called as mutual induction. So here current is increasing in this coil, let us say. So there will be a change in the flux in this coil. Because of the change in the flux in this coil, current is induced in this coil, and not only that, this coil is placed close to this, so current can also be induced in the second coil. So this is called as mutual induction. Or when because of the current that is induced here, an EMF that is induced in the first coil, then that is called as also is called as mutual induction. See, that is what we are writing here. Let us consider two coils that are placed near to each other. When current is passed in the primary coil, the first coil, I am considering it as primary coil. So there is a change in the magnetic flux linked with it. So an induced EMF is set up in the secondary coil. Or when there is a current that is passing through the secondary coil, when the EMF is set up in the primary coil, then that phenomena is known as mutual induction. So mutually they are related. That is why that concept is called as mutual induction. So in this mutual induction also, the flux that is produced in a coil is always directly proportional to the current. But the current that is passing through the secondary coil. Okay, two coils will be there. The flux that is generated in one coil is directly proportional to the current that is passing through the secondary coil. And if you remove this proportionality, we get a constant. In the self-induction concept, there is a change in the flux in the coil. So current is induced in the same coil. That is why the proportionality constant we wrote it as L. But here, the flux that is generated in one coil due to the change in the current in other coil, or you can say due to the change in the flux in one coil, current is induced in the other coil. So that is why if we remove the proportionality, we write a constant M, which is called the coefficient of mutual induction or mutual inductance. So the mutual inductance is the flux linked with a circuit due to the unit current passing through the other. How I can say the unit current? See, if I substitute I equals to 1 ampere here, I can write phi B equals to M. So, the coefficient of mutual induction or mutual inductance is the flux that is linked with a coil when 1 ampere current passing through the other coil. This is one definition, and the other definition we can give using this equation. According to Faraday's law, we know that the induced EMF is minus d phi by dt. But from this equation, phi is what? Mi. So if I substitute that equation in this, you will get E equals to minus d mi by dt. M is constant, we cannot differentiate. So write outside. So minus m di by dt we get. Now to define this mutual inductance, consider this di by dt as 1, just like self-induction, but there is L, here it is M. There is only one coil, here there are two coils. Change in the flux in one coil EMF is generated in the other coil. There in self-induction, change in the flux in one coil. Due to that, induced EMF is generated in the same coil. That is the difference. So here, consider di by dt equals to 1 to define this M, mutual inductance. So if di by dt is 1, I can write M equals to E. See, only magnitude I am taking because this negative sign indicates the direction of this EMF. It opposes the original cause. So only magnitude if I take E is M di by dt. If this di by dt is 1 ampere unit change in the current, then M is E. So how I can define this mutual inductance? Mutual inductance is equal to EMF induced in a coil or circuit when the rate of change of current is unity in the other coil. That you have to mention, other. In a coil, there is a induced EMF that is developed. Due to what? Due to the rate of change of current is 1 ampere in the other coil. So that is called as coefficient of mutual induction, or we can also call it as mutual inductance. Now the next topic is mutual inductance of a solenoid. Just like how we have discussed the self-inductance of a solenoid, we are going to discuss about mutual inductance of a solenoid. Mutual inductance is what? When current is passing in one coil, EMF is generated in the other coil. Or when current is passing in the other coil, EMF is generated in the first coil. That means we need to take two coils. So that is why in order to derive the expression for mutual inductance of a solenoid, let us consider there are two solenoids. So S1 is first solenoid, S2 is the second solenoid. The solenoid S1 is placed inside the second solenoid. So this is the first solenoid. It consists of N1 number of turns. So the total number of turns in first solenoid is N1. And this is placed inside the second solenoid. This second solenoid consists of N2 number of turns. So the total number of turns in solenoid S2 is N2. R1 is the radius of the first solenoid. R2 is the radius of the second solenoid. L is the length of both the solenoids. So here N1, N2 are total number of turns that are present in first solenoid and second solenoid respectively. This is not equals to small n1. Small n1 is what? Number of turns per unit length. That is small n1 is capital N1 by L, because L is the length of the solenoid. So N1 be the number of turns per unit length in the first solenoid. N2 be, small n2 be the number of turns per unit length in the second solenoid. Let us consider, we know when there is a change in the flux in one solenoid, current can be induced in the second solenoid. Or when there is a change in the flux in the second solenoid, current can be induced in the first solenoid. That is the concept of mutual induction. So that is why first I am considering, let phi1 be the magnetic flux that is developed in coil S1 due to the current passing through the second coil I2. So here current that is passing through the second solenoid is what? I2. So because of the current that is passing through the second solenoid, flux is developed in the first solenoid. That is what mutual induction. So what we can write? N1 phi1 is directly proportional to I2. I2 is what? Current passing through the second coil or second solenoid. Due to that, flux is generated in the first solenoid. And the number of turns in the first solenoid is N1. So the total flux that is developed in the first solenoid is N1 So that is depending on what? Due to current that is passing through the second solenoid. So I can write N1 is directly proportional to I2. Now, if we remove this proportionality, we know we will get a constant. So remove this proportionality, write the constant. So here the constant, I am not writing it as M. It is M12. Why M12? We have already written here. Flux that is developed in S1 due to current that is passing through S2. That is why we write it as M12. So what is M12? M12 is mutual inductance of solenoid S1 due to S2. Due to this current that is passing through S2 only, flux is developed in the solenoid S1. So that is why this constant here it is M12. Consider this as equation 1. And we know the magnetic flux phi is B into A. This is the expression for magnetic flux. So now what is the total magnetic flux that is there in the first solenoid that we are calculating? So there are number of turns N1. So N1 phi1, that is total flux in this solenoid S1 is B into A. What is B? It is magnetic field induction due to a solenoid. So what is the magnetic field induction due to the solenoid? We know the expression for the magnetic field induction due to the solenoid is mu naught Ni. But here I wrote it as mu naught N2 I2. Why mu naught N2 I2? Because flux is generated due to what? Due to the current that is passing through the second solenoid. That is why the magnetic field is mu naught N2 I2. Area is pi r square. Area of the solenoid, it is pi r1 square into N1. N1 is total number of turns in the first solenoid, and that is equals to number of turns per unit length into L. So we get mu naught N2 I2 pi R1 square N1 L. So the product of these two, on simplifying this equation, we get mu naught N1 N2 I2 pi R1 square L. Consider this as equation number 2. From equation 1, we got N1 phi1 as M12 I2. From this equation 2, I got N2 phi1 as mu naught N1 N2 I2 pi R1 square L. So we can compare these two equations. If I compare these two equations, we get M12 I2 equals to mu naught N1 N2 I2 pi R1 square L. So that is what you can see here. M12 I2 equals to mu naught N1 N2 I2 pi R1 square L. So on LHS side we have I2, and on the right hand side also we have I2. So these two will get cancelled. So on simplifying this equation, we get M12 equals to mu naught N1 N2 pi R1 square L. Consider this as equation number 3. So here we have considered current that is passing through second solenoid. Due to that, flux is developed in the first solenoid. But now mutual induction. So what I am taking? Current that is passing through the first solenoid due to the flux that is developed in the second solenoid. So current is passing in the first solenoid and flux is developed in the second solenoid. So now what is the flux that is developed in the second solenoid? We have to find out. So the flux that is developed in the second solenoid is depending on the current that is passing through the first solenoid. That is what mutual induction. So how much is the flux that is developed in the second solenoid? It is also depending on the number of turns in the second solenoid. In one turn, it is phi2, but in solenoid S2, there are N2 turns. So the total flux is N2 phi2, which is developed in the second solenoid. It is directly proportional to current passing through the first solenoid. So N2 phi2 is directly proportional to I1. And if you remove the proportionality, we get a constant. Here that constant is not M12, it is M21. Why? Flux is developed in the second coil due to current that is passing through the first coil. So it is called as mutual inductance of solenoid S2 due to S1, due to the current that is passing through S1. So we got one equation. Now, from the magnetic field induction, what is flux we will see. So the flux that is linked in the second solenoid is N2 phi2 equals to the same expression, because flux is magnetic field induction into area. So that is what we have taken. And B is a magnetic field induction due to a solenoid. That is mu naught Ni. But here, current that is passing through the first solenoid, that is why the magnetic field induction due to that solenoid is mu naught N1 I1. Area of cross section is, I am taking it as pi R1 square, because solenoid S1 is inserted in solenoid S2. So the radii is almost equal. So in general, we can write pi R square also. So here the same thing, I am taking pi R1 square, and capital N2 is small n2 into L. Then on multiplying this, we get N2 phi2 equals to mu naught N1 N2 I1 pi R1 square L. So in this equation we got N2 phi2, and in this equation also we got N2 phi2. So from both the equations, on comparing these two equations 5 and 6, what we can write? M21 I1. That means I am substituting this in this equation in place of this N2 phi2. I can write M21 I1. So M21 I1 equals to mu naught N1 N2 I1 pi R1 square L. So here I have I1. This side also I have I1. So these two will get cancelled. Then after simplifying, M21, which is the mutual inductance of solenoid S2 due to S1, is mu naught N1 N2 pi R1 square L. See, if you see equation 3 and equation 7, M12 is what? Mutual inductance of solenoid S1 due to solenoid S2. M21 is mutual inductance of solenoid S2 due to S1. Both are equal. You can see. So this is mu naught N1 N2 pi R1 square L. This also mu naught N1 N2 pi R1 square L. So we can write both M12, which is mutual inductance of solenoid S1 due to S2, equals to M21, which is mutual inductance of solenoid S2 due to S1. As both are equal, that we can take it as M. So what is the expression for mutual inductance of a solenoid? It is mu naught N1 N2. This area in general we can write it as pi R square L. So this is the expression for mutual inductance of a solenoid. This is the last topic of this chapter, and the important questions in this chapter are Faraday's laws of induction. It is very, very important. They will ask you to write the laws of Faraday's law. They will ask you to write Faraday's laws. So you have to write these two, and Lenz law also very important. You know, according to Lenz law, the direction of induced EMF is, it opposes the original cause that produces it. And they can also ask you to write what are eddy currents, applications of eddy currents. Any two applications they can ask. And the concept of self-induction and mutual induction also very important. They can ask you to define what is self-inductance. Any one definition you can write. Here 3 definitions that are given. Any one definition you can write. And what is mutual inductance. So all these concepts are important in this chapter. Thank you.